Find somewhere comfortable tonight. If you are already in bed, let your body settle a little deeper into whatever is holding you. You do not need to follow this closely. You do not need to remember any of it. If the words arrive and drift past like clouds, that is exactly right. If you fall asleep before we reach the end, that is not a failure. That is the whole point. Tonight we are going somewhere cold. Colder than the surface of Mars. Colder than the dark side of the moon. We are going to a place where the ordinary rules of electricity quietly stop applying, where something happens to matter that took humanity more than 40 years to even begin to explain, and where the strangeness of the quantum world becomes, somehow, visible. A small disk of ceramic floating in midair above a magnet, patient and still, held up by nothing you can touch. We will move through 8 chapters tonight, each one a room to wander through rather than a lecture to follow. The science here is genuine and deep, but it arrives slowly, the way understanding tends to arrive when you are not forcing it. The night is long, and we are in no rush to reach its end. So let the shoulders drop, let the jaw soften, let whatever you were carrying today grow a little more distant, the way sounds outside a window fade when you stop listening for them. We begin in a laboratory in the Netherlands in the year 1911 on an ordinary April morning that turned out to be anything but. There is a particular kind of scientist who is less interested in theories than in the physical world itself, who wants to touch the edges of what is possible, to push a measurement further than anyone has pushed it before, and to see what happens when you get there. Heike Kamerlingh Onnes was that kind of scientist. He was meticulous, almost obsessive, and he had spent the better part of 2 decades building in Leiden, in the southern Netherlands, what was arguably the most sophisticated low-temperature laboratory in the world. He called it his factory of cold, and the name was not entirely metaphorical. Producing extremely low temperatures in the early 20th century was an industrial undertaking, requiring vast apparatus, skilled technicians, and a kind of patient, methodical determination that most scientists simply did not have. What Onnes was after was absolute zero. Not quite. He knew that absolute zero, the point at which all thermal motion ceases, cannot actually be reached, only approached, but he wanted to get closer to it than anyone had managed. Absolute zero sits at minus 273.15 degrees on the Celsius scale, or 0 on the Kelvin scale, a unit named in honor of the physicist William Thomson, Lord Kelvin, who first proposed the concept of a lowest possible temperature. Every degree Kelvin above 0 represents 1 degree of thermal energy, of atomic jostling and vibration, still present in a material. The closer you push towards 0, the stiller everything becomes. In 1898, the Scottish chemist James Dewar had liquefied hydrogen, reaching around 20 Kelvin. That was cold enough to win him considerable fame. But hydrogen was not the coldest gas available. Helium, the lightest of the noble gases, boils at just 4.2 Kelvin under normal atmospheric pressure, and nobody had managed to liquefy it yet. Onnes spent years designing the apparatus that would do it, a cascading series of refrigeration stages, each one using the cold produced by the previous stage to cool the next gas down further, step by patient step, until the final stage could compress and expand helium until it crossed its boiling point and became liquid. On the 10th of July 1908, it worked. One must produce the first liquid helium ever seen on Earth. A small, still pool of colorless fluid sitting in a glass vessel, cold enough to freeze the air itself if any leaked in. The temperature in that vessel was approximately 4.2 Kelvin, 4 degrees above the coldest temperature the universe permits. He had reached further from ordinary warmth than any human experiment before him. For the next few years, Onnes turned this extraordinary cold toward a question that had been puzzling physicists for some time. What happens to the electrical resistance of a metal as it approaches absolute zero? This is worth thinking about for a moment because resistance is not an abstract property. It has a physical cause that is wonderfully concrete once you understand it. A metal conductor is, at the atomic level, an orderly crystal lattice, a regular, repeating three-dimensional grid of positively charged ions, the atomic nuclei stripped of some of their outer electrons. Those freed electrons do not belong to any particular atom. They float through the lattice like a sea, a vast crowd of negatively charged particles moving in response to any electric field applied across the material. When you connect a battery to a copper wire, what you are really doing is nudging this sea of electrons in one direction, creating a slow, coordinated drift. That drift is the electric current. But the lattice is not still. Temperature is, at the atomic scale, nothing more than vibration. Every ion in the lattice is shaking, oscillating back and forth around its equilibrium position, and the warmer the metal, the more violently it shakes. And those drifting electrons, moving through this forest of jostling ions, collide with them constantly. Every collision deflects an electron, robs it of some of the momentum it was carrying, and releases that energy as heat. This is electrical resistance. It is friction at the scale of atoms. The energy you put into driving a current through a resistive wire does not all arrive at the other end. Some of it is lost to this constant, churning collision process, warming the wire as it goes. Now, if temperature is vibration and resistance comes from vibration, then a reasonable hypothesis is that cooling a metal should reduce its resistance. As the ions slow down, they present a smaller target, and electrons can drift through more freely. By the late 19th century, experiments had confirmed this trend. Metals do become less resistive as they are cooled. But the question of what happens at very low temperatures was genuinely open. Some physicists thought resistance would continue falling smoothly toward zero as the temperature approached absolute zero. Others thought it would level off at some small but non-zero value, because even at absolute zero there would still be impurities and structural imperfections in the lattice to scatter electrons. And a few thought resistance might actually rise again at very low temperatures for reasons related to the quantum behavior of electrons that were only beginning to be understood. Onnes chose mercury for his first careful measurements, partly because it was easy to obtain in very pure form. Impurities were one of the competing variables he wanted to eliminate, and partly because its resistance at room temperature was well characterized. He set up his apparatus to cool a thin thread of mercury in a sealed glass tube, and he measured its resistance as the temperature fell, degree by careful degree, toward the boiling point of liquid helium. The resistance fell, as expected. It fell steadily and smoothly. And then, at 4.2 Kelvin, the same temperature at which helium itself becomes liquid, it did not merely become small. It vanished. Not faded to a very low value, not approached zero asymptotically, always getting closer but never quite arriving. It dropped within a temperature range of only a few hundredths of a degree from a measurable value to something his instruments could not detect at all. The resistance of mercury at 4.2 Kelvin was, as far as Onnes could tell, exactly zero. He was, by all accounts, initially suspicious of his own result. A reading of zero on an instrument can mean the thing you are measuring is zero, or it can mean your instrument has failed, or your circuit has a short somewhere, or your thermometer is wrong. He checked everything. He found the same result each time. The resistance of mercury below 4.2 Kelvin was not approximately zero. It was zero. He called this new state of matter superconductivity, a material conducting electricity with super, meaning beyond normal, perfection. In 1913, he received the Nobel Prize in Physics, partly for this discovery and partly for the liquefaction of helium that had made it possible. His acceptance speech described the vanishing of resistance with a quiet precision that, even read a century later, carries the weight of genuine wonder. But what does it mean truly for resistance to be zero? Not small, not negligible, zero. The electrons are still there, the lattice is still there, the current is still there, and yet the friction between them has stopped entirely. Something has changed in the nature of the electrons themselves, something so fundamental that the ordinary rules of collision and energy loss simply do not apply anymore. For now, in 1911, Onnes had a result that was clean and extraordinary and deeply, deeply strange, sitting in his laboratory like a question that would take half a century to answer. The mercury thread, cooled to 4 degrees above absolute zero, was carrying electricity with no resistance at all, a river without banks, without friction, without end. Picture a loop of wire, not a circuit with a battery at one end and a light bulb in the middle, just a loop, a closed ring of conducting material with nothing else attached. If you start a current flowing in that loop and then leave it alone, what happens? In an ordinary copper ring, the answer is straightforward and a little melancholy. The current begins to decay almost immediately. The electrons, drifting around the ring, collide constantly with the vibrating lattice ions, losing momentum with every encounter. Each collision is a small theft of energy, and the cumulative effect of billions of these thefts per second is that the current weakens, and within a fraction of a second it has fallen to nothing. The ring sits there, silent, all that kinetic energy dissipated as a faint warmth in the copper. Without a battery continuously pushing electrons around, the current simply cannot sustain itself. Now cool the ring below its critical temperature, cool it into the superconducting state. The same current, started in exactly the same way by briefly exposing the ring to a changing magnetic field and then removing the source, does not decay. It flows around the ring, and it keeps flowing, not for a second, not for an hour, not for a day. Experiments have been done in which superconducting rings were set oscillating with a current and then monitored for years. Years! The current did not measurably diminish. Physicists have calculated, based on the precision of those measurements, that if a current were started in a superconducting ring and left entirely alone, it would still be flowing, at the same strength, without any power source, after 1 million years, after 10 million years. The universe would look very different by then, but the current would still be going around. This is not a theoretical extrapolation made with hand-waving optimism. It is a consequence of the measured upper bound on the resistance of a superconductor, which experiments have placed at less than 1 part in 10, followed by 26 zeros of the resistance of copper. That is not approximately zero. For any practical purpose, it is indistinguishable from perfect zero, and the persistence of the current follows as a mathematical certainty. But to understand why the resistance is zero, truly zero, not just very small, we need to sit with what a current actually is at the atomic level, and then understand what changes when a material crosses into the superconducting state. In an ordinary metal, the electrons carrying the current are independent particles. Each one moves through the lattice on its own, influenced by the electric field that is driving it, but also constantly buffeted by the thermal vibrations of the lattice ions around it. The average speed of an electron in a metal at room temperature is actually enormous, roughly 1.5 million meters per second, a significant fraction of the speed of light, driven by the quantum mechanical energy all electrons carry regardless of temperature. But this motion is completely random in direction, a frantic, chaotic pinball game. The net drift velocity, the slow, coordinated movement of electrons in one direction that constitutes the current, is tiny by comparison. In a typical copper wire carrying ordinary household current, the drift velocity of electrons is around 1 millimeter per second. 1 millimeter per second. The electrons are moving at 1 million meters per second in random directions, and only a tiny, tiny bias in one direction constitutes the current. Every collision with a lattice ion randomizes an electron's direction slightly, stealing a little of that bias, and the resistance you measure is the cumulative effect of all those small redirections. Now think about what happens as you cool a metal. Cooling reduces the thermal vibrations of the lattice. The ions shake less violently and they present a smaller effective obstacle to the drifting electrons. Resistance falls. In very pure metals cooled to a few Kelvin, resistance can fall to around 1/10,000th of its room temperature value. But it does not reach zero. There are always some impurity atoms, always some defects in the crystal structure, always some source of scattering. The resistance asymptote stored a small but non-zero flaw. In a superconductor, something entirely different happens at the critical temperature. It is not merely that the lattice vibrations have become quieter. The electrons themselves have changed their behavior. They have stopped being independent particles. And this is the key. An independent electron moving through a lattice can always be scattered, deflected by an impurity, by a vibrating ion, by any small irregularity in its environment. But what if the electrons are no longer independent? What if they are linked together into a collective entity so vast and so coherent that the small perturbations of a single lattice ion are simply not powerful enough to deflect it? That collective entity is what exists in a superconductor below the critical temperature. The electrons are paired, and the pairs are locked together in a shared quantum state, moving as a single coordinated whole. A single electron can be scattered, the entire collective cannot. This is why resistance is not merely reduced but eliminated. The mechanism that causes resistance, the scattering of individual electrons, no longer applies to the thing that is actually flowing. The critical temperature is the threshold at which this collective state becomes possible. Above it, thermal energy is too high. The heat in the lattice is vigorous enough to break the partnerships before they can form, and the electrons remain independent, colliding and scattering as usual. The pairing becomes energetically favorable. The collective state condenses, and the river begins to flow without friction. Every superconducting material has its own critical temperature, its own threshold below which this transformation occurs. For mercury, it is 4.2 Kelvin. For lead, it is 7.2 Kelvin. For the alloy niobium titanium, which is used in most modern superconducting magnets, it is around 9 Kelvin. For the most exotic materials discovered in the 1980s and beyond, it can be above 90 Kelvin. But in every case, the critical temperature represents the same physical boundary. Above it, ordinary resistance. Below it, the river that never slows. There is also a critical magnetic field to consider. The superconducting state is not only sensitive to temperature, it is also sensitive to the strength of any magnetic field threading through the material. Above a certain field strength, the superconducting state is destroyed, even if the temperature is well below the critical temperature. This is because magnetic fields interact with the electrons in ways that disrupt the partnerships that make superconductivity possible. The critical field is different for different materials, and understanding why some materials can tolerate far stronger fields than others became one of the central practical questions of the field. Because the most useful applications of superconductivity, the powerful electromagnets in MRI machines, in particle accelerators, require both low temperature and the ability to carry enormous currents in strong magnetic fields without losing the superconducting state. But these details, the critical field, the critical current, are refinements on a central, simple, almost meditative fact. The current flows. It flows without loss. It flows without effort, without cost, without end. There is something in that image that is worth holding quietly for a moment. The idea that motion, once started, need not inevitably decay. That a river, given the right conditions, does not have to run dry. The mystery that Onnes left behind him was not just a curiosity, it was a deep theoretical puzzle that sat at the center of physics for nearly half a century. Here was a phenomenon, electrons flowing through a material with zero resistance, That clearly required an explanation at the microscopic level, at the level of what individual electrons and atoms were actually doing. And yet every attempt to construct that explanation ran into the same fundamental obstacle. Electrons repel each other. They carry the same negative charge, and like charges push apart. The force between two electrons follows the same inverse square law as gravity, only in the opposite direction. The closer they are, the more strongly they push away from each other. So any theory of superconductivity that required electrons to pair up, to form some kind of cooperative partnership, seemed to be starting from an impossible premise. How do you get two things to stick together when their most basic property is mutual repulsion? The answer, when it finally came in 1957, was one of the most elegant pieces of physical reasoning in the 20th century. It came from three American physicists, John Bardeen, Leon Cooper, and Robert Schrieffer, and it hinged on something that at first seems completely unrelated to electrons, the vibrations of the crystal lattice itself. To understand their insight, you need to hold in mind a picture of what a metal's crystal lattice looks like. The atoms in a metal are not randomly distributed. They are arranged in a precise, repeating three-dimensional pattern, like an enormous stack of oranges at a market, each atom sitting in a fixed relationship to its neighbors. The atoms in this lattice are not the neutral atoms you might picture from chemistry class. They have given up some of their outer electrons to the collective sea of conduction electrons, so they are positively charged ions, each one sitting at its lattice point and vibrating gently around it, the way a ball on a spring oscillates around its resting position. Now, here is the crucial insight. These vibrations are not independent, because each ion is connected to its neighbors through the electromagnetic forces between them. A vibration in one part of the lattice sends ripples through the whole structure. These ripples travel through the crystal as waves, mechanical waves like sound waves, but at the atomic scale. And here is where the quantum world enters. Just as light is both a wave and comes in discrete packets called photons, these lattice vibration waves also come in discrete packets. Each packet of vibrational energy has a definite size, a quantum of vibration. Physicists call these quantiphonons, from the Greek word for sound, just as photons are named for light. A phonon is not a particle in the ordinary sense. It has no mass of its own. It is a ripple of coordinated atomic motion propagating through the lattice, and it carries a definite amount of energy and momentum, just as a photon does. Phonons are responsible for how heat travels through a solid, among other things. But their role in superconductivity is something altogether more subtle. Here is the mechanism step by step, because each step is worth understanding fully. An electron is moving through the lattice. It is negatively charged, and the lattice ions around it are positively charged. As the electron passes through a region of the lattice, it attracts the nearby ions slightly toward it. Just a tiny displacement, a small puckering of the lattice inward around the electron's path. This distortion is not permanent. The ions are spring-connected to their equilibrium positions and will snap back. But the snapping back takes time. The ions have mass, and mass means inertia, and inertia means the response is slow compared to the electron's own motion. So the electron moves through, leaving behind it a region where the lattice is slightly compressed, slightly more dense with positive charge than it was before. This distortion propagates outward through the lattice as a phonon, a ripple of displacement, spreading away from the electron's path like a wake behind a boat. And as it spreads, it carries with it that slight excess of positive charge drawn inward by the electron's passage. Now, a fraction of a millisecond later, which at the scale of electron motion is actually quite a long time, a second electron comes along. It is following a path that brings it into the region where the first electron's wake is still fading, and in that region there is a slight excess of positive charge. The second electron, being negatively charged, is attracted to that excess positive charge. It is drawn toward the corridor left by the first electron's passage. The result is a net attraction between the two electrons, mediated by the phonon. The first electron polarized the lattice, and the second electron responded to that polarization. They never needed to be close to each other. In fact, by the time the second electron arrives, the first has long since moved on. The attraction is indirect, delayed, mediated by the lattice vibrations between them, but it is real. And at low temperatures, where the thermal jostling of the lattice is quiet enough not to disrupt this delicate process, the phonon-mediated attraction can actually overcome the direct electrostatic repulsion between the two electrons. The timescale here is worth dwelling on. The lattice distortion persists for roughly 1/10 of a second, 1 picosecond, in the language of physics, before the ions return to their equilibrium positions. An electron moving at its typical speed travels several hundred nanometers in that time. So the two electrons in this partnership are not close together in space. They are separated by hundreds of nanometers, perhaps as much as 1,000 nanometers in some materials. To give you a sense of scale, atoms in a metal lattice are spaced about 1/4 of a nanometer apart. The two paired electrons can be separated by a distance equal to several thousand atomic spacings. They are a vast distance apart by the standards of the atomic world, and yet they are linked by this phonon-mediated correlation. These partnerships are called Cooper pairs, named for Leon Cooper, who in 1956 showed mathematically that even a very weak attractive interaction between electrons near the surface of the Fermi Sea, the boundary between filled and unfilled electron energy states, would be sufficient to cause pairing. This was the key theoretical step before the full BCS theory was assembled. Cooper showed that the attraction did not need to be strong. It just needed to exist. Cooper pairs are not tightly bound, the way the two atoms in a hydrogen molecule are bound. They are loosely correlated, spread across an enormous distance, each electron going about its own business in the lattice while remaining quantum mechanically linked to its partner. The binding energy of a Cooper pair is tiny, on the order of 1,000th of an electron volt, which is about 1,000,000 times smaller than the energy binding electrons to atoms. This is why the superconducting state is so fragile. A small increase in temperature provides enough thermal energy to break these pairs apart, returning the electrons to their independent, scattering, resistive state. But below the critical temperature, in the cold and the quiet, the phonon whispers are enough. The lattice speaks to the electrons in a language of vibration, and the electrons, listening across vast distances, find each other. So we have pairs, billions upon billions of Cooper pairs, distributed throughout the superconducting material, each one a loosely bound partnership of two electrons mediated by the lattice vibrations between them. But having pairs is not, by itself, enough to explain zero resistance. To understand why resistance vanishes entirely, we need to go one level deeper, into a distinction that sits at the very heart of quantum mechanics, the difference between two fundamental types of particles and what happens when you cross the boundary between them. Everything in the universe is made of particles, and quantum mechanics divides all particles into two great families based on a property called spin. Spin is an intrinsic angular momentum that every particle carries, a kind of built-in rotation that exists even when the particle is not moving through space. Spin comes in multiples of 1/2, and this seemingly technical detail has consequences that reshape the entire structure of matter. Particles with half-integer spin, 1/2, 3/2, and so on, belong to the family called fermions. Electrons are fermions with a spin of 1/2. Protons and neutrons are also fermions, and fermions obey a rule that Wolfgang Pauli identified in 1925. No two fermions can occupy the same quantum state at the same quantum state, at the same quantum state, at the same quantum state at the same time. This is the Pauli exclusion principle, and it is the reason atoms have the structure they do. Electrons cannot all pile into the lowest energy level, so they stack up in shells, and the arrangement of those shells determines all of chemistry. Particles with integer spin 0, 1, 2 belong to the other family called bosons. Photons are bosons with a spin of 1, and bosons obey the opposite rule. They are not merely permitted to share a quantum state, they actually prefer to. The more bosons you put into a particular quantum state, the more likely additional bosons are to join it. This is the quantum mechanical basis for lasers, where billions of photons are coaxed into exactly the same state of light, and for many other phenomena. Now, a Cooper pair is made of 2 electrons. Each electron is a fermion with spin 1/2. When you combine 2 spin 1/2 particles, the total spin of the combination is either 0 or 1, both of which are integers. A Cooper pair therefore has integer spin. It is a boson. Not a fundamental boson, but a composite one, made of 2 fermions that have paired up. And this crossing of the boundary, from the fermion world of electrons to the boson world of Cooper pairs, changes everything. Below the critical temperature, something remarkable happens to these composite bosons. They undergo what physicists call Bose-Einstein condensation. This is a process predicted theoretically by Satyendra Nath Bose and Albert Einstein in 1924 and 1925, though not observed in the laboratory until 1995, in which a collection of bosons, cooled below a critical temperature, all fall into exactly the same quantum ground state. Not a range of similar states, the exact same single quantum state. To feel the weight of this, consider what a quantum state is. Every particle in quantum mechanics is described by a quantum state, a mathematical object that encodes everything about the particle's position, momentum, energy, and other properties. In an ordinary gas or liquid, each particle has a different state. They are distributed across a vast range of energies and momenta, each one doing its own thing. In a Bose-Einstein condensate, all the particles share one state. They lose their individual quantum identities. They become, in a very precise sense, a single entity. In a superconductor below the critical temperature, all the Cooper pairs condense into the same quantum ground state. There can be an enormous number of them. In a piece of superconducting wire a centimeter long, there are on the order of 1 billion Cooper pairs, and all of them, every single one, is described by the same quantum wave, not similar waves. The same wave, spread across the entire material, coherent from one end to the other. This coherence is the key to zero resistance. Here is why. When a lone electron moves through a lattice, it can be scattered, an impurity atom sitting in the lattice. A foreign atom that does not belong to the crystal structure presents an obstacle. The electron's wave hits the impurity, and some of the wave bounces back, some goes sideways, and the net drift of the electron is disrupted. A lattice vibration, a phonon, can also scatter an electron, transferring some of the electron's momentum to the lattice. These scattering events are what resistance is made of. But now consider the Cooper pair condensate, the single quantum wave that encompasses all the pairs simultaneously. For a scattering event to deflect this wave, it would need to deflect all the pairs at once in a coordinated way. A single impurity atom, or a single phonon, interacts with the condensate, but the condensate is so large, so coherent, so deeply settled into its ground state that the small perturbation from a single scattering event is simply absorbed without effect. You cannot scatter one Cooper pair out of the condensate without simultaneously affecting all the others, and the energy required to do that is much larger than what a single phonon or impurity can provide. There is also a related concept called an energy gap, which is worth understanding because it reinforces the same idea from a slightly different angle. In the superconducting state, there is a gap in energy between the ground state of the condensate and the lowest excited state, the state you would need to push a Cooper pair into in order to break it. This gap is small but definite. At temperatures below the critical temperature, the thermal energy available, the random jostling of the lattice, is not large enough to bridge this gap. So the pairs cannot be broken, and the condensate cannot be disrupted. It sits in its ground state, immovable, and the current flows through it unimpeded. The image that comes to mind is something like a vast, slow river, not a collection of individual water molecules moving separately, each one jostling against rocks and eddies, but a single body of water moving as a whole, smooth and unhurried, too large and too coherent to be stopped by any individual obstacle. That is what the Cooper pair condensate is. A single quantum wave spread across an entire piece of metal, carrying a current that nothing in the material structure can deflect. Onnes saw the river. He measured it with his instruments and confirmed that it was real. But the image of it, a billion pairs of electrons moving in perfect unison, described by one wave that spans the whole material, flowing without end, that image had to wait half a century before physics could provide it. If you were to take a small piece of lead, a soft, grey, heavy metal, and cool it below its critical temperature of 7.2 Kelvin, something happens that goes beyond the vanishing of resistance, something that is, in its own way, even more striking. If there is a magnetic field present, even a weak one, even the faint magnetic field of the Earth itself, that field is expelled, not blocked, not merely prevented from entering, expelled, actively pushed out of the interior of the superconductor, even if it was already there before the cooling began. The superconductor crosses its critical temperature, and the magnetic field lines which had been threading through the material are physically ejected, pushed to the outside, leaving the interior of the superconductor in a state of perfect magnetic emptiness. This is the Meissner effect, named for Walther Meissner and Robert Oxenfeld, who first observed it in 1933. And it is important to understand why this is surprising, why it is not simply what you would expect from a material with zero resistance. Think about what a perfect conductor would do. A perfect conductor, a hypothetical material with zero resistance but no special quantum properties, would, by the laws of electromagnetism, preserve whatever magnetic field was inside it at the moment it became perfectly conducting. If a magnetic field was present when the material became perfectly conducting, the field would be frozen in place, because any change in the magnetic field would induce currents in the perfect conductor that would exactly oppose the change. And since those currents experience no resistance, they would persist indefinitely and keep the field constant. A perfect conductor locks in the magnetic field that was there when it became perfect. A superconductor does something different. It does not merely lock in the existing field. It actively expels it, regardless of whether the field was present before or after cooling. Cool. A superconductor in the presence of a magnetic field, and the field is pushed out. Cool it in the absence of a field, and then bring a magnet close, and the field is prevented from entering. The end state is the same. The interior of the superconductor is field-free. The mechanism behind this expulsion is elegant. As the material crosses its critical temperature and the Cooper pair condensate forms, currents spontaneously arise on the surface of the superconductor. These are not driven by any battery or external source. They arise because the quantum mechanical state of the condensate requires it. The surface currents flow in precisely the right pattern to generate a magnetic field inside the superconductor that exactly cancels the external field. The cancellation is perfect, not approximate. The interior field is reduced to zero, and the external field is pushed into the space around the superconductor, where it bulges and curves around the material like a river around a stone. These surface currents are persistent currents, just like the current in a superconducting ring. They flow without resistance, and they flow for as long as the superconducting state is maintained. The practical consequence of this is the phenomenon of magnetic levitation. If you place a small permanent magnet above a superconductor, the superconductor's surface currents generate a magnetic field that exactly mirrors and opposes the magnet's field. The magnet is repelled. And if the geometry is right, the repulsion can be strong enough to support the weight of the magnet, holding it floating in midair, perfectly still, with no mechanical contact and no energy input. This is not a trick or an approximation. It is a direct consequence of the Meissner effect, of the superconductor's insistence on maintaining a field-free interior. There is a refinement to this picture that becomes important when you move from pure metals to more complex materials. Pure metals, lead, mercury, tin, aluminium, are called type 1 superconductors. They expel magnetic fields completely up to a certain critical field strength, and then, if the field exceeds that threshold, superconductivity is destroyed entirely and abruptly. The transition is sharp. Below the critical field, perfect expulsion. Above it, ordinary metal. The critical fields for type 1 superconductors are generally quite low. For lead, it is around 0.08 of a Tesla, which is a fairly weak field. This means type I superconductors cannot be used in applications that require strong magnetic fields because the field itself would destroy their superconductivity. Type 2 superconductors behave differently, and their behavior is both more complicated and more useful. They are generally alloys or more complex compounds rather than pure elements. A type 2 superconductor has not one but two critical field values. Below the lower critical field, it behaves exactly like a type 1 superconductor. Complete expulsion of the magnetic field, perfect Meissner effect. Above the upper critical field, superconductivity is completely destroyed, just as in type 1. But between those two values, something interesting happens. In this intermediate range, the magnetic field does not simply penetrate the material uniformly. Instead, it enters in the form of discrete, quantized tubes of magnetic flux, tiny channels, each one carrying exactly the same amount of magnetic flux, the same definite quantum of field. These tubes are called flux vortices, or sometimes Abrikosov vortices, after the Russian physicist Alexei Abrikosov, who predicted them theoretically in 1957. Each vortex is a thin cylinder of normal, non-superconducting material surrounded by a circling superconducting current that contains the magnetic field within the tube. The rest of the material, outside the vortices, remains fully superconducting. The quantization of the flux in each vortex is a direct consequence of the quantum mechanical nature of the Cooper pair condensate. The condensate is described by a single quantum wave, and the consistency requirements of that wave, the requirement that it return to exactly the same value after going around a complete loop, mean that the magnetic flux through any loop in the condensate can only take specific discrete values, multiples of a fundamental unit called the flux quantum. Each vortex contains exactly one flux quantum. The practical importance of type 2 superconductors is enormous. Because they can tolerate much stronger magnetic fields, the upper critical field can be tens of Tesla or more in some alloys, hundreds of times larger than the critical fields of type 1 materials. They can be used in applications where powerful magnetic fields are required. The superconducting magnets in MRI machines, in particle accelerators, in experimental fusion reactors are all made from type 2 superconductors. The alloy niobium titanium, cooled to around 4 Kelvin in liquid helium, can carry enormous currents in fields of many Tesla without losing its superconducting state. This is the workhorse of applied superconductivity, winding through the bore of every clinical MRI scanner in the world, carrying currents of hundreds of amperes around and around without losing a single watt to resistance. The Meissner effect, then, is not merely a curiosity or a party trick with levitating magnets. It is a fundamental signature of the superconducting state, as deep and as definitive as zero resistance, and the distinction between type 1 and type 2 behavior, between complete expulsion and the subtle quantist threading of flux vortices, opens the door to the entire practical world that superconductivity has made possible. In 1962, a 22-year-old graduate student at Cambridge named Brian Josephson sat down to think carefully about what would happen if you placed two superconductors very close together, separated by a thin layer of insulating material. Not touching, separated by a gap, perhaps a nanometer or two wide, thin enough to be invisible to any ordinary instrument, but still, by classical physics, an impenetrable barrier. Electrons, in the classical picture, cannot pass through an insulator. They lack the energy to cross the gap. So two superconductors separated by an insulating layer should be electrically isolated from each other. The Cooper pair condensate in one unable to reach the other. Josephson knew, however, that electrons are not classical particles. They are quantum mechanical objects, and quantum mechanical objects do not have sharp, definite boundaries. They are described by waves, probability waves that extend through space and diminish as they move away from the particle's most likely location, but never quite reach zero. Even on the far side of a barrier that a classical particle could not cross, the wave has a small but non-zero value, and where the wave has a non-zero value, there is a non-zero probability of finding the particle. This phenomenon, the ability of a quantum particle to appear on the far side of a barrier it classically cannot cross, is called quantum tunneling. The name is intuitive. The particle seems to tunnel through the barrier rather than going over it. Quantum tunneling is not a rare or exotic effect. It underlies nuclear fusion in stars, the operation of the tunnel diodes used in electronics, and the mechanism by which certain chemical reactions proceed at low temperatures. But Josephson was thinking about something more specific. Could the Cooper pair condensate tunnel through an insulating barrier? Not just individual electrons, but the entire coherent quantum wave of paired electrons. His calculations showed that it could, and not only could it tunnel, it would tunnel in ways that were precisely predictable and deeply strange. The first prediction was this: if the two superconductors on either side of the barrier are at exactly the same voltage, a supercurrent, a current of Cooper pairs, would flow through the barrier with no voltage applied at all. Zero voltage difference, non-zero current. This is the DC-Josephson effect, where DC stands for direct current. It happens because the quantum wave of the condensate on one side bleeds through the barrier and overlaps with the condensate on the other side, and the two condensates can exchange Cooper pairs through this overlap without any driving force. The current depends on the phase difference between the two condensates, a quantum mechanical property of the waves that describes their relative alignment, and it oscillates as a function of that phase. The second prediction was even more remarkable. If you apply a small voltage across the barrier, a constant, steady voltage, the current flowing through it does not become a steady, direct current. Instead, it oscillates. The current alternates back and forth many billions of times per second with a frequency that depends on the voltage in an exact, precise, universal way. The frequency is proportional to the voltage, and the constant of proportionality involves only two fundamental constants of nature: the charge of the electron and Planck's constant, the fundamental quantum of action. This is the AC-Josephson effect, where AC stands for alternating current. Josephson published his predictions in 1962. The experimental physics community was initially skeptical. Some prominent physicists doubted the analysis. But within 2 years, both effects had been confirmed experimentally. Josephson received the Nobel Prize in Physics in 1973, sharing it with two other pioneers of quantum tunneling phenomena. He was, at the time of the award, 33 years old. The device that Josephson's effect inspired is called a SQUID, which stands for Superconducting Quantum Interference Device. A SQUID consists of two Josephson junctions, two thin insulating barriers, connected in parallel by a loop of superconducting wire, The current flowing through this loop is exquisitely sensitive to the magnetic flux threading through the loop, because the magnetic flux affects the phase difference across each junction, and the phase difference controls the current. By measuring the current, you can infer the flux, and because the flux is quantized in units of the flux quantum, you can measure magnetic fields with extraordinary precision. How precise? A CUYD can detect magnetic fields as small as a few femtotesla, that is, a few millionths of a billionth of a Tesla. To put that in perspective, the Earth's magnetic field is around 50 microtesla, about 50 millionths of a Tesla. The magnetic field produced by the electrical activity of the human heart is roughly 10 picotesla, 10 trillionths of a Tesla, a million times weaker than the Earth's field. The magnetic field produced by the electrical activity of the brain, by the currents flowing through neurons as they fire, is around 100 femtotesla, 100 millionths of a billionth of a Tesla. That is what a squid can measure. The technique that uses SQUIDs to map the brain's magnetic activity is called magnetoencephalography, a word that means, roughly, measuring the magnetic field of the brain. An MEG scanner is a helmet-shaped device lined with hundreds of SQUID sensors, each one cooled to liquid helium temperature and positioned close to the patient's scalp. As neurons fire inside the brain, the tiny electrical currents they carry generate magnetic fields that extend slightly outside the skull. The SQUIDs detect these fields, and by recording from many sensors simultaneously and applying mathematical analysis, researchers can construct maps of which regions of the brain are active at each moment in time, with a temporal resolution of around 1 millisecond, fast enough to track the dynamics of individual neural events. MEG is used clinically in the investigation of epilepsy, helping surgeons locate the precise region of the brain where seizures originate before they operate. It is used in research to study the neural basis of language, of perception, of memory, and of sleep. The slow oscillations of deep sleep, the delta waves that sweep across the sleeping cortex in great, slow waves, cycling between half a cycle and 4 cycles per second, have been mapped in detail using MEG, revealing the precise choreography of neural silence and activity that characterizes the deepest and most restorative phases of the night. There is something quietly beautiful in this chain of connection. Josephson, a young Cambridge student, reasoning about quantum waves and insulating barriers. Cooper pairs tunneling through a nanometer-thin gap, a magnetic field 100 millionths of a billionth of a Tesla, produced by a cluster of neurons in a sleeping brain. And the SQUID, sitting at the intersection of these scales. Quantum mechanics at its most delicate, made into an instrument precise enough to listen to the brain's own magnetic whisper. From the coldest laboratory in the world to the intimate electrical life of the mind, the same physics, all the way down. For decades after Onnes's discovery, superconductivity seemed to be a phenomenon permanently confined to the very deepest cold. The highest critical temperature known in the early 1980s was around 23 Kelvin, achieved in an alloy of niobium and germanium. This was still far below the boiling point of liquid nitrogen, 77 Kelvin, which would have been the natural threshold to aim for because liquid nitrogen is cheap, safe, and abundant. Liquid helium, which all practical superconductors of that era required, is scarce, difficult to produce, and expensive. Using it requires elaborate insulation, careful handling, and a continuous supply. The gap between 23 Kelvin and 77 Kelvin seemed, to most physicists, likely to be permanent. The theoretical framework of the time, the BCS theory, the phonon mechanism, suggested that critical temperatures much above about 30 Kelvin were essentially impossible for conventional superconductors. In 1986, that certainty was quietly shattered. Georg Bednorz and Alex Muller were working at the IBM Research Laboratory in Zurich, Switzerland. They were not mainstream superconductivity researchers. Müller was a specialist in a class of materials called perovskites, complex ceramic oxides with a particular crystal structure, and he had a hunch, based on his knowledge of how electrons interact with the lattice in these materials, that they might be worth exploring for superconductivity. Ceramics are, in ordinary experience, electrical insulators. Think of pottery, of porcelain, of the ceramic coating on electrical wiring. The idea that a ceramic might be a superconductor seemed almost paradoxical. But Bednorz and Müller were patient and methodical, and in early 1986 they synthesized a particular ceramic compound, a mixture of lanthanum, barium, copper, and oxygen belonging to the class of materials now called cuprates, and measured its electrical resistance as a function of temperature. At 35 Kelvin, the resistance dropped sharply. Not to zero. The samples were not quite pure enough, but the signature was unmistakable. Something superconducting was happening in a ceramic at a temperature that BCS theory said was essentially impossible. They published their results in April of 1986 with characteristic understatement in a paper whose title included the phrase possible high TC superconductivity. The response from the physics community was initially muted, then rapid, then frantic. Within months, groups around the world were synthesizing their own versions of the material and confirming the result. And then, in early 1987, Qing-Wu Chu and his collaborators at the University of Houston made a modification to the crystal structure, replacing the lanthanum with yttrium in a compound of yttrium, barium, copper, and oxygen, and found that the critical temperature jumped to 92 Kelvin. 92 Kelvin, above the boiling point of liquid nitrogen. The significance of this threshold is difficult to overstate. Liquid nitrogen boils at 77 Kelvin. It is produced in enormous quantities as a byproduct of the industrial process that separates the components of air. It is used in food preservation, in medicine, in manufacturing. It costs, at the time of writing, roughly the same per liter as milk. Cooling a superconductor with liquid nitrogen rather than liquid helium is not merely cheaper, it is qualitatively different. It is the difference between a technology that requires specialized infrastructure and constant expert attention, and one that could, in principle, be made practical and widespread. The announcement of the 92 Kelvin result in early 1987 sent a shock through the physics world that is hard to convey in retrospect. The American Physical Society's March meeting that year became known as the Woodstock of Physics. Thousands of researchers crowded into a hotel ballroom in New York at midnight to hear presentations on the new high-temperature superconductors, a session that ran until dawn. Bednorz and Müller received the Nobel Prize in Physics in 1987, one of the fastest awards in the prize's history. Within the following years, critical temperatures in cuprate ceramics climbed further still, to 138 Kelvin in mercury. Kelvin in mercury barium, calcium copper oxide, a record that stood for decades. And then the field ran into a wall. Not a wall of experimental difficulty, but a wall of understanding. Because nobody could explain why these ceramics superconduct. The BCS theory, the phonon mechanism, the Cooper pairs, the condensate, is a beautiful and precise theory, and it works extraordinarily well for conventional superconductors. But when physicists applied it to the cuprates, they found that phonon-mediated pairing could not possibly account for critical temperatures as high as 90 or 130 Kelvin. The phonon mechanism is simply too weak at those temperatures. Something else must be providing the attractive interaction that pairs the electrons. But what that something else is has been debated, investigated, and argued over for nearly 4 decades without consensus. The cuprates have a layered structure, sheets of copper and oxygen atoms separated by layers of other elements. The electrons responsible for superconductivity move primarily within these copper-oxygen planes, and their behavior is strongly influenced by the magnetic interactions between them. In a cuprate, neighboring electrons tend to have their spins pointing in opposite directions, a property called antiferromagnetism, and this magnetic ordering is intimately connected to the superconducting state, appearing and disappearing as the material's composition is varied. Many physicists believe that fluctuations in this magnetic ordering, spin fluctuations, ripples in the magnetic arrangement of the electrons, play the role that phonons play in conventional superconductors, providing the glue that binds Cooper pairs together. But the mathematical treatment of spin fluctuations is enormously more complicated than the phonon theory, and the calculations are not yet precise enough to definitively confirm or rule out this picture. Another possible mechanism involves the way electrons hop between different energy bands in the material. In some theoretical models, Cooper pairs form by resonating between two different electronic states, analogous to the way certain chemical bonds resonate between different configurations in molecules like benzene. This interband pairing can, in principle, produce much higher critical temperatures than single-band phonon pairing, but demonstrating it conclusively in the cuprates has proven elusive. Perhaps the most intriguing clue is a phenomenon called the pseudo-gap. In many cuprate superconductors, if you raise the temperature above the critical temperature back into the apparently normal resistive state, you find that the material does not behave like an ordinary metal. Some of the signatures of superconductivity persist. There is still a gap in the electronic energy spectrum, still some evidence of electron pairing, still something unusual about the way the material conducts electricity, even though the resistance is no longer zero. This pseudo-gap phase, the name means false gap, because it resembles but is not quite the same as the gap in the true superconducting state, extends to temperatures well above the critical temperature, and understanding it is widely considered the key to unlocking the mystery of high-temperature superconductivity. One picture is that the pseudo-gap represents a state in which Cooper pairs have already formed, but they have not yet condensed into the coherent, unified quantum wave that produces zero resistance. The pairs exist, but they are incoherent. Each pair has a random phase relative to all the others, so they do not add up to a collective current. Below the critical temperature, the phases lock together, the condensate forms and resistance vanishes. Above the critical temperature, the pairs are still there, but disordered. This would mean that the critical temperature in cuprates is not set by the energy required to form pairs, as it is in BCS superconductors, but by the energy required to bring the pairs into phase coherence. If true, this would require a fundamentally new theoretical framework. The mystery of high-temperature superconductivity is not a small gap in knowledge waiting to be filled. It is one of the central unsolved problems in condensed matter physics. The study of how large numbers of atoms and electrons behave collectively. Understanding it would not merely explain a curious phenomenon. It would deepen our understanding of quantum many-body physics, of how electrons in strongly interacting systems organize themselves, and it might open the path to designing superconductors with even higher critical temperatures, perhaps eventually reaching the dream of room temperature superconductivity. That dream is still alive. It is pursued in laboratories around the world, patiently, in the cold and the quiet, with instruments of extraordinary sensitivity and theories of enormous complexity. The ceramic that surprised everyone in 1986 is still, nearly 4 decades later, keeping its deepest secret. The world that superconductivity has built is, for the most part, invisible. It hides inside machines, behind panels, beneath floors, at temperatures far below anything you will ever feel. But it is present, quietly, in some of the most important places in modern life. In every hospital that has an MRI scanner, and there are tens of thousands of them, in every country where modern medicine is practiced, there is a superconducting magnet. It is a large, cylindrical structure, usually white, with a bore through its center, just wide enough to slide a patient through on a table. Inside the walls of that cylinder, wound in careful coils, is a wire made of niobium and titanium. an alloy chosen for its ability to carry large currents in strong magnetic fields while remaining superconducting at liquid helium temperatures. The wire carries a current of several hundred amperes, enough to power a small town's worth of appliances, around and around in a continuous loop, generating a magnetic field of 1.5 to 3 Tesla in the bore of the magnet. This field is what allows the MRI machine to do its work, aligning the hydrogen nuclei in your body's water molecules and then listening to the radio waves they emit as they relax. The crucial point is that this current does not need a power supply to maintain it. Once the magnet is charged, a process that takes several hours and requires a careful, controlled ramp-up of the current, the superconducting loop is closed and the current circulates indefinitely. A large hospital MRI magnet might run for a decade or more on the same persistent current, never losing a measurable fraction of its field, never requiring the enormous power that would be needed to maintain the same field in a resistive electromagnet. The magnet does need to be kept cold, which requires a continuous supply of liquid helium or a powerful mechanical refrigerator, but the electrical energy to maintain the field itself is essentially zero. This efficiency is not merely convenient, it is what makes clinical MRI possible at all. A resistive electromagnet producing the same field would consume megawatts of electrical power and would need to be the size of a building. The superconducting magnet fits in a room and draws only the power needed for its cooling systems. The persistent current is not just a curiosity from a physics lecture. It is the reason you can have a detailed image of a brain tumor, a torn ligament, a compressed disc, without radiation, without surgery, without anything more than lying still in a gentle magnetic field. 15 minutes outside Geneva, buried 30 meters underground in a roughly circular tunnel, 27 kilometers in circumference, is the Large Hadron Collider at CERN. It is the largest machine ever built, and it runs on superconductivity. The tunnel is lined with approximately 9,600 superconducting dipole magnets, each one a curved 2-meter-long assembly of niobium titanium coils, cooled to 1.9 Kelvin, colder even than the temperature of deep space, by superfluid helium. These magnets generate fields of about 8.5 Tesla, used to bend 2 counter-rotating beams of protons around the ring at velocities within a tiny fraction of the speed of light, until the beams are brought together at collision points where the protons smash into each other with energies that recreate conditions from the earliest moments of the universe. Without superconducting magnets, the Large Hadron Collider could not exist in its current form. The fields required to bend particles moving at those energies around a ring of that size are too large to be produced by any resistive electromagnet at an acceptable cost of electrical power. Superconductivity is not an enhancement to the machine, it is the enabling technology. The Higgs boson, whose existence was confirmed at CERN in 2012 after decades of searching, was found in a machine that runs on Cooper pairs. In Japan, on a test track in the Yamanashi prefecture, a magnetic levitation train called the SC Maglev has reached a speed of 580 kilometers per hour, the fastest any passenger vehicle has ever moved on land. The train carries superconducting magnets in its undercarriage, cooled to liquid helium temperature, generating powerful magnetic fields that induce currents in aluminium loops set into the guideway. Those induced currents create a lifting force that holds the train about 10 centimeters above the track, eliminating all mechanical contact and therefore all friction between train and guideway. At operating speed, the train floats in a magnetic field, propelled by a linear motor touching nothing. The silence inside the cabin, by all accounts, is remarkable. Then there is the dream that has not yet been achieved, and the attempts to reach it. In 2020, a research group reported in the journal Nature that a compound of hydrogen, carbon, and sulfur, compressed to around 2.5 million times atmospheric pressure, became superconducting at approximately 15 degrees Celsius, above the freezing point of water, within the range of ordinary room temperature. This would have been an extraordinary result, Superconductivity at temperatures that require no cooling at all, only the enormous pressure of a diamond anvil cell pressing a tiny sample from both sides. The paper generated considerable attention. In 2022, it was retracted after questions arose about how the data had been processed and presented. The retraction did not prove that room temperature superconductivity at high pressure is impossible, only that this particular evidence for it was unreliable. In 2023, a team of South Korean researchers announced that a material they called LK99, a compound of lead, copper, phosphorus and oxygen, was a room temperature superconductor at ambient pressure. No cooling, no compression, just a ceramic sitting on a laboratory bench. Videos circulated of a small piece of the material appearing to partially levitate above a magnet, and for a few weeks in the summer of that year, the physics world held its breath. Dozens of laboratories around the world attempted to replicate the result. By the end of the year, the consensus was clear. LK99 is not a superconductor. The apparent levitation was traced to a different property of the material, and careful measurements showed that its resistance, while unusual in some ways, did not reach zero. The episode was disappointing but not dishonest. The original researchers appear to have been genuinely mistaken rather than deceptive, and it demonstrated both the hunger for a room temperature superconductor and the rigor with which such claims are scrutinized. The dream persists. It is not obviously impossible. Theoretical work on hydrogen-rich compounds under pressure has suggested that, under the right conditions, the phonon-mediated pairing mechanism can be made strong enough to produce critical temperatures approaching room temperature because hydrogen's light mass allows it to vibrate at very high frequencies, and high-frequency phonons can in principle mediate stronger pair attractions, and in principle mediate stronger pair attractions. The challenge is the pressure. 2.5 million atmospheres cannot be achieved in any practical device, but understanding why high-pressure hydrogen compounds superconduct at such high temperatures might reveal design principles that could be applied to materials that work at ambient pressure. And so the search continues, patient and unhurried, in laboratories where liquid helium drips and diamond anvils press, and instruments listen for the moment when resistance becomes zero. The science of superconductivity began with a measurement, a number that should have been small but was not. It was zero, exactly, impossibly, beautifully zero. And in the century and more since that April morning in Leiden, it has grown into a landscape of extraordinary richness. Cooper pairs and condensates, Meissner effects and flux vortices, Josephson junctions and squids, ceramic crystals that should not work but do, and the persistent unresolved question of why they work. It is a science of quiet extremes, of temperatures so low that the ordinary rules of matter give way to something stranger and more orderly, of currents that flow forever without a source, of magnetic fields expelled by the sheer coherence of a quantum wave. And perhaps that is why it feels, in the deep of the night, like something worth thinking about, not urgently, not with effort, just holding the image gently, a river of electrons, paired and coherent, flowing through a cold, dark wire, undiminished for 1,000,000 years. There is something the sleeping brain knows about coherence. In the deepest hours of the night, when the day's noise has finally quieted, the brain does something similar to what happens in a superconductor. The delta waves, those slow, deep oscillations cycling between half a cycle and 4 cycles per second, begin to spread across the cortex, not chaotically, not in fragments. They sweep in great, slow, coordinated waves, one after another, like a tide coming in. The billions of neurons that spent the day firing in rapid, independent, effortful patterns begin to move together. The friction of wakefulness, the constant, lossy, resistive work of thinking and deciding and reacting gives way to something more coherent, more unified, more still. It is not the same as superconductivity. Brains are warm and wet and governed by chemistry rather than quantum mechanics, and the analogy is loose. But there is something in the image that resonates across the distance between physics and sleep, The individual gives way to the collective. The chaotic gives way to the coherent. The resistive gives way to something that flows without friction, without effort, without loss. Whatever you were carrying today, whatever resistance you moved through, whatever collisions you absorbed, you do not need to carry it into the night. The day is already behind you, already growing distant and quiet. The waves are moving slowly now, spreading from one edge of the mind to the other, patient and deep and unhurried. The river is still flowing. Let it carry you.